So yesterday we saw how the loss function um, is an expression of the model parameters, so all the weights from W0 to WP, and the expression for that is um, basically the least square estimate. So on this side um, of the equation, what you have here is the predicted output for a particular observation I. Okay, so this is a linear model we have, and this is the actual data we know is true. And we do the sum of square differences between the predicted value and the output, and what we get is the loss function, which is the least square. And we saw that this is a function of your weights, and at the minimum of E, we must have these conditions. So the gradient of E respect of all the parameters is 0. And we saw that by explicitly deriving this expression for each of the weight parameter, then you get basically a system of, here we have P+1 equations. Okay? Rewriting these equations, as we saw yesterday, just develop here. We can see, so all the weights are expressed here, and the terms you have, the coefficients, okay, only depends on the features you have about the the observations, and therefore it's something you can compute quite easily offline. Okay, and same here, you have the outputs, yi, and the features. But all these are elements you can compute online. So it's quite simple enough. You have a system of P+1 equations, and you can solve that using linear algebra. Okay. What I'll show you is how to derive these equations using matrix notations. And the reason why we want to do this is because it's way more practical, and it'd be much closer to what you have to do. So if you have to write a linear solver in Python, sorry, least square estimate in Python, this is you have to use the matrix notations basically. So in terms of notations, okay, so if I have by convention, okay, I use cursive letters for scalar. I'll use upright letters for vectors, okay? And so here, x would be a vector of x1 and xp, okay? And I use capital X for matrices, okay? So capital X would be a matrix like that. Sorry, more n1 and p. Okay, so that's kind of notation. So scalar vectors matrices. Okay, and so let's see what we have in our case. Okay, so these are for notations. Okay, so what we have in our case is sorry, just move that away. So in our case, the list of all the features, okay, so we have our linear model, and I say for again, I'll write it again. So the outcome for sample 1 is W0 plus W1 xi1 plus so on to WP xip. Okay, so this is the PS features. Okay. All right. Just to simplify things, matrix notation and everything, so we have P+1 terms here, and it'd be more practical for us if we say that we collect all the features as being, so the first feature associated with W0 will be actually 1, and then we have x1 and xp. Okay, so the observation we have, say, for the ES sample will be xa. So once again, 1 xi1 and xip. Okay, so this is a vector, okay, and of size p plus 1 times 1. Okay, so p plus 1 is the number of elements you have on the number of rows you have, and 1 is the number of columns you have. Okay, we can concatenate all this information into what's called the design matrix, capital X. And the design matrix basically is a matrix where each column will contain all the features for all the instances of a particular feature. So this looks like this. So you have all the ones on the first column, and then you have x11, x1p, and then you go down here to x21, x2p, and you keep on going to xn1, and here you have xnp. Okay, so this big matrix, all it does is to just stack all this information about the features and the ones we have here. And other way of writing it is to say it's a concatenation of the feature vector for the first observation and just a transpose of it, and you keep on doing like that for all your observations. Okay, so remember, x1 transpose is it's just this guy, but in a horizontal way. So that would be 1, 1, x1p. Okay. It's just really, this guy is just really this row here. Okay. And similarly, we have y, upright y, which contains all the outcomes. So y1 to yn. Okay. And you can have epsilon here, which would be our error, which would be epsilon1. Okay. So remember, epsilon, should say epsilon1 is actually the difference between the predicted value. So there'll be y1 hat minus sorry, like this, the other way around, and so that's y1 minus the expected value of our system. So w minus w1 x11 minus and so on minus wp x1p. Okay. All right. So we've defined the design matrix X. Okay. So I'll just write that again to design matrix. We've designed the output x, y, and the input vectors xi's. Okay, and of course we can do the same. We can have the all the vectors set together as well. Okay. So let's come back to our mean square error. So the loss function. So remember. The loss function now is a function of a vector of these weights, and it's really very much the same as what we have here. Okay, so these two terms are the same, except this is, if you want, just a vector w. And we said that it was 1 over n of the sum for all the elements. Okay, so this is n of all the elements for the difference between the predicted outcome and the actual outcome squared. All right, so this is the minimum squared error. Okay, or the squared error. Sorry, that will be the real term. So in other way, this is the sum over all my examples of the squared error I have. Okay. Now in matrix notation, it turns out that you can write that this is actually in matrix notation. You can write that as epsilon transpose epsilon, where epsilon is the vector we talked about. Okay. So indeed, so epsilon transpose will be a vector like this, okay, to be a horizontal vector, and then you have epsilon, which is a vertical vector, okay. And when you start to do the multiplication, you first go from you multiply epsilon 1 by epsilon 1, then you move on, then you multiply epsilon n by epsilon n. So really, this will be something like that. So sum over I from 1 to n of epsilon I squared. Okay, so indeed, this matrix notation is equivalent to that version. Okay, so from that point on, we have a matrix expression for the loss function. So we have our loss function is 1 over n of epsilon transpose epsilon, and we can plug in what we know about epsilon. So this is so on the side. So remember we have y. So our linear model was y is xi transpose w. Okay, and so the real linear model was combined together. We have y is x, which is design matrix, times w. Okay, so and plus epsilon. So I should have done that before, but basically, yes, the predicted value for each of my so you have a feature vector, so you have an observation, and this turns out to be equals to exactly what we talked about. So it's really so xi transpose is 1, xi1 xip, and this one is w0, w1, and wp, and we do the sum. This is really equals to w0 plus w1 xi1 plus and so on and so forth to wp xip, which is exactly linear model. Okay, so this is a matrix notation for a prediction, and this is the matrix notation for the entire model for so here it's basically you have n equations really. Okay, so these are n equations stacked together in a single linear expression. Okay, so from that point on, you realize that okay, epsilon is just y minus xw. Okay, so I can plug that in. So I can say this is y minus xw transpose y minus xw. Okay, and it's all fine. So I mean, I can develop that. I can do a lot of things. So that would be y transpose times y, and so I have y transpose minus xw, and I have minus y transpose x transpose y, and then last one will be plus w transpose x w. Okay, so this is the expression you have for it. Okay. All right, so we have a matrix expression for the least square estimate. Now, the same way we said that a sufficient condition, necessary condition to reach the minimum. So we need to say at the minimum, okay, we must have the partial derivative for each of the weights equals 0. Okay, this is necessary, and remember the argument goes like so. If you're just working in 1D, then your loss function will necessarily at the minimum have a slope which is horizontal. Okay, so if that is so we imagine there's only it's just a scalar here. Then at the minimum, we know we have the derivative of that function, which is 0. Okay. And the same argument goes for n-dimensional space, so it has to be true for every single of these variables. So it turns out, okay, that instead of manipulating all there's a matrix formulation for the partial derivative, and it's called the gradient. Okay, and now it turns out there's two notations for it. So you can say, it's gradient of E, and there's a similar definition which is just like that. Okay, except this time W is a vector. Okay, so it's a vector. Okay, and so both notations are found. I mean, you can have sometimes the gradient, so it's the inverted triangle here. Okay, so the inverted triangle indexed by W of E. Okay, and both work. I have a preference for this one. I'll use this one. Okay, and all what it is here. Okay, so you have you have this gradient according to W. So remember, this guy is a scalar. Okay, so it's a function of W. Okay, and the function returns a scalar, and we've taken the gradient of that, and all it is here is just the vector. Sorry, the vector according to all of its parent components. Okay. I would just take the partial derivative for each of the weights, and we'll just stack that into a vector. As a side note, you can take the gradient of according to pretty much anything. Okay, so you could imagine that if your loss function. Okay, so it's a bit a side note here, but say you have a loss function which is function of a matrix A, and like for completeness, say it's B transpose A B, where B is a vector. Okay, so that quantity here is a scalar, and it's fine. It's a function of a matrix. Okay, and you have that. Well, you can compute no problem the partial derivative according to A, and all it is just a matrix, the same shape as A, that contains the partial derivative according to every single each of the elements of your matrix. Okay, so the concept of a gradient, okay, is just like you have a set of values that are shaped in the form of a vector, and you want to compute the derivative according to each of these values. And so this is what you have. You have this function of a number of parameters, and you want to compute the gradient according to these guys. And it's basically, if you can do the derivative according to one of the elements, then you're fine to go. Okay, you just do that for all the elements, and then reshape whatever the list of all the results you get for the derivative into the same shape as W. Okay? And you can do the same with matrices and so on. But don't worry, we won't have to work with matrices, just with vectors. Okay, so coming back, okay? So what we have the loss function, okay, expressed in the matrix form. And what we say is we want to have the gradients according to W, the weights, to be 0. And this time 0 is actually the vector of all these zeros. And you have p plus 1 zeros at this point. Okay? So, so this is what we want to solve. So let's do that, okay? All we need to know to do is, really to be able to do the one for every single one of those guys. Now, it turns out, okay, there are formulas for how to compute the gradients, and I should have one in the slides, and let's look at what you have in the slides. So it's here. They're just like results. Okay, you can plug in whatever situation you have in here and apply it. So I'd say these guys are important, and this one is a bit more obscure. So forget about it. Okay. But basically, what it says here is like, okay, if my error, let's take this example here. Okay. So my loss function here is of this form, okay, and all it is here is it says like it's of this form, okay. So it's A transpose W, so it's a sum of AI and WI, okay, because that's really 1 to AP and ZW 1 to WP, okay. So this is how you do the computation, and this is the form you have, okay. Now, obviously, if you do the partial derivative of this guy according to, say, WK, so just any of the WKs, then it turns out there's only one WK, only one term here that has a WK, and that term has a coefficient AK, okay. So the partial derivative of this one derivative of this guy according to WK is just AK, okay, because all the other terms will be cancelled out. Because we have that for every single K, that means that the gradient according to W is all my A1 AP, okay, and that's exactly just A. Okay, that's your vector A. So this is the relationship. Okay, so we have proved that the gradient of this expression according to W is indeed just A, and that's just the expression there. So all these are just like results you don't even have to worry about deriving yourself. They're just handy results for you. Okay, so let's use those to try to solve our problem. And so I put them on the side here, and let's do that. Okay, so we have the first term, if you want, is we need to compute the gradient is a linear operation. So this will be 1 over n of the gradient of y transpose y. So you can, it's linear, you can distribute it, please. And then you will do the gradient of that expression, and then you have the gradient of that other expression, sorry, transpose y, and then you have the gradient of W transpose X W. Okay, and you say it's 0. And because it's 0, I'm just going to cancel this guy in front. It doesn't really matter. Okay, so the first term, y, well, it doesn't depend on W. I mean, y is it's an input, but it's not input, it's the outcome, and it's fixed, okay? That's whatever the real outcome was. So that's 0. And then there's this term here. So if you look back here, so y transpose X is actually a vector. So that would be our B, or your A transpose right here. So really we identifying this expression. So if I plug in this expression, I will get my gradient. And so that will give me minus, so I have to be careful to, here there's no transpose, so I need to transpose this guy, so that'll be X transpose Y, okay? And here we can do the same, and it's actually times 2, that's right? Yeah, no. And it actually is the same, it's X transpose Y, and this term here is identified here, where A, if you want, is your X transpose X matrix. So let's say we have plus X transpose X plus X transpose X transpose of W equals 0. Okay, so it turns out that X transpose X transpose is, it's X transpose and then X transpose transpose, but that's actually just X. So that X transpose X, and basically it's the same, okay? So X transpose X is the transpose of it is actually the same matrix. So it means that X transpose X is symmetric. Okay, so we have the gradient of the loss function is equal to a vector of zeros, and it's equal to minus 2 X transpose Y plus 2 X transpose X, these two guys, times W. Okay, and you put things in the right place, and you have X transpose X times W equals X transpose Y. And this is, again, the normal equations. And if you come back to the previous slides we had, this is exactly the same expression as this one. Okay, so when you basically plug in the what X is and W and so on, when you develop that, you have here a linear system of equation that says that at the minimum X must satisfy, W must satisfy this equation, okay? And this is the same as this equation, okay? So basically, remember that X, your design matrix, looks like this. Okay, so if you do X transpose X, you obtain a matrix of size, well, it's P plus 1 in this case, and P plus 1. And each of the entries here is something in the form sum of xi j, xi k, yeah, something like that. So okay, so the entry ij had this shape here, okay, and basically these are the entries of your matrix. Okay, so you have x transpose x, so that's a matrix. Okay, and that coefficient here corresponds in this particular instance to I1p. Okay, this one will be a PP. Okay. All right, so this is the expression you get. Okay, so once again, these are all equivalent. Okay, we haven't done anything new. It's just we express everything in terms of linear algebra and using matrix notations. Okay, so let's have a look now. Let's come back on our problem. Okay. So coming back to the slides. This was the data, and we had only one feature, okay, which was the height, and the outcome was the weights. Okay, so this is how you will go about to approach this problem. Okay, so this is kind of the practical strategy you need to adopt. Okay, so the first thing to do is to say, I have a problem. What is the model I have for this problem? Okay, so in this case, we say that the outcome, so the weight, okay, so that's weight, is some W0 plus W1, weight 1 of x, and x is actually the height, okay. And that's the assumption you make, okay. You say that I can predict the y, and the weight as a linear, it's something times the height plus something else. Okay, so that's your assumption. That means that your feature vectors, okay, so W0, the feature associated with that is actually 1, and the feature associated with the W1 is x1, so it's the height for the sample 1, okay? And so when we stack all these features in the design matrix, we have 1 x1 and so on, 1 xn. Okay, so ones and the heights for each of the individuals. Then we compute x transpose x, which is the matrix you need to solve, to invert, sorry, and that gives you a 2x2 matrix. So here you have 2 by 2 elements. And then you have x transpose y, which is the other element we need to have. And then you solve the least square estimate by inverting this matrix and multiplying by this other vector. And this is the fully developed version of that. But you never really have to write this way. I mean, what you do is you just, in Python, you will define in NumPy a matrix, okay, so there will be here n by 2 matrix, and once you have x defined, then you just, and y is defined, then you just compute w hat directly from that equation, okay, and that gives you the answer. And in this case, the answer is just a straight line that goes through all your data, okay. Now, here's a very important point, okay, and this is where least square is going to be useful for the subsequent activities we will have in this module, okay. You have to understand that we use here a linear model, and by linear it means that we effectively have, we say that the outcome, or at least the predicted outcome, is a linear combination of the features, all right? But the features don't necessarily need to, they can be anything, okay? And they don't need to be linear. I mean, they don't have to be, they can be whatever you want. So if you want to have a polynomial model, like if you want to fit a polynomial to your data. Okay, so the polynomial is nonlinear, but it is linear of the basis function. Okay, so here you have w0 times 1 plus w1 times x, and then here we've added, kind of the same way we've added a 1 here, we add 2 extra features, x squared and x cubed. Okay, and these x2 and x3 are derived from the feature x, so there's nothing really new there, but what we're doing here, we're kind of enhancing the set of features. I mean, we set it from 1 feature, and now we have 4 features. We have 1x, x squared, and x cubed. And the hope is that the outcome could be explained as a linear combination of these 4 features. Okay, so it's very important. Okay, so the linear limitation is not as bad as you would think. Okay, because you have total freedom on how you design your features. For instance, you could say that y is a combination of 1 plus something cosine of x and sine of x, for instance. Okay, it could be anything, and obviously this is highly nonlinear in x, but that doesn't matter. What matters is it linear in the weights w0, w1, and w2. Okay, so it's all you have to be creative about how you transform your features and how you choose your features. So here's an example of that. So you have a small data set here with a few points, and obviously the real model is the following. Okay, so it's actually a polynomial of order 2. So it's a parabola. Okay, and the ground truth here, the dotted line. So to find the coefficient of that parabola, we need first to set the model. So okay, we know the model, it's this guy. Okay, so we then need to populate the design matrix, and we say, well, each feature for each observation we have 3 features, and so it would be 1, x, and x squared. Okay, I will just populate that for every single of your observation. So you have n observations, so you have n rows, and you have 3 features, so 1, x, and x squared, so that's matrix of n by 3. Okay, so when you estimate the least square, then what you get is the so the x transpose x matrix is then 3 by 3 components. You have 9 elements here, and this is 3 and 1. Okay, it's always going to be 3 by 1 and p by 1. Okay, so the beauty here is you don't have to, when you design the code for the least square estimate, the matrix notation, the core of the algorithm is still the same. You just have to plug in that formula using linear algebra packages. The only thing that has to change is the way you design your matrix here. Okay, design matrix. But the formulation, the formula is still the same, remains the same regardless of what you have. So, sorry. So this is what it looks like. Okay, so the dotted line, very fine here, is the ground truth, and you can see that the estimated model, the solid red line, is a pretty nice fit. And it is true. What we've computed here is basically the least square error. So the mean square error. So the mean square error would be 1 over n of our estimated predicted value minus what we actually observe for the ground truth. Okay, so that's a small number enough. Okay. Now this is what happens when you use the wrong model. Okay, so let's say we have some data, but we actually don't know what relationship, how this works. So maybe we just say, well, we just take our data and just try to fit a line. Okay, and obviously if you fit a line, it's not very good, right? I mean, the points are quite far from this line, and in this case, the mean square error is much bigger. Okay, so this would be the distances to this line that you have, and this is a classic problem, and it's called underfitting. Okay, it's something that is going to be seen, and it's a problem general to any machine learning technique. Okay, so underfitting it's something you have. It's ubiquitous. Okay, so every single machine learning algorithm you can run into the problem of underfitting. Okay, so how do you know that you are underfitting? So remember, underfitting means that your model is maybe not quite powerful enough or not flexible enough to actually model your data. Okay, and you know that you're underfitting if you find that your loss function. Okay, so remember this is actually your loss function. It's not going down enough. Okay, so here the mean square error is quite high. I mean, it's much higher than what we had before. Okay, so for the correct model, we had it at around 0.5 or something like that of error, and here it's 200. Okay, now the scale or the actual magnitude is really depends on your problem, but on your application, but you will know. Okay, you would say, I try to train that. I use all my observations and I try to fit the data, and it just didn't work very well. Okay, you don't get on the data you have a good prediction. If that happens, chances are you're actually underfitting, or in other words, that your model is really not representing what you have. I mean, you're not doing the right thing. Okay. The other problem you have is overfitting. Okay, so that's the the other side of the spectrum. So in this case, what you say, right? Okay, we made a terrible job with just fitting a linear line. Let's go and have a polynomial of order 9. Okay, and let's make sure everything is fine. And then in this case, sure enough, right, every single point in your training set, okay, in the data you have given to the system, actually fits perfectly well. I mean, if you look at the error here, it's perfect. Okay, so that's your loss function here is really good. Okay, I mean you're doing tremendously good. So surely nothing is wrong, but obviously it's very much wrong. Okay, and what happens? Okay, to detect that is if you give new examples, and especially if you take a new point that is quite far away from the original training set. So these points that you use for the estimation, okay, they all come from something called the training set. Okay, so if you use a new point, okay, so something new here, and you test against your model, you will find that it's way up high over somewhere very far, and obviously you're going to make a gross error on that prediction. And if you find that, so it's a simple way. I mean, evidence that you're overfitting is that if you're doing very well on your loss function, it's very low on your training data. So every time you give a point from your training set, just prediction is perfect. But every time you take a new point that is outside of that training set, if it's grossly wrong, then you're probably overfitting. Okay, so it means that you took a model and you make it perfect for the training data, but not so much perfect for the rest. Okay, so next time, so the last part of the course, we're going to see how you try to techniques to overcome overfitting.